Okay, so question 8. Two rigid boxes, A and B, are placed next to each other on a flat, rough floor. The masses of the boxes are 20 kilos for A, 20 kilos, and 12 kilos for B. Force of 248 newtons is applied to the box from the left as shown. The size of the friction force increases with the mass of the box. So friction, show the size of the friction force on the box. Okay. So force due to friction is equal to 4.51 times by the mass, because this is 4.51 newtons per kilogram. So for this one, it's just 4.51 times by 12. 4.51 times by 12 is equal to 54.1 newtons. So you've shown. The friction force is 90.2. Determine the acceleration of box A. So the net force is equal to the force applied, which is 248, minus our friction forces. So it says the friction force for box A is 90.2, but we've also got to subtract the 54.1 newtons for the friction on B, and that gives us 103.7 newtons. We can then go F equals MA. Now the mass is the combined mass, so that's equal to 32. Because 12 plus 20, so that's 32. Times by A, and that's equal to our net force, which is 103.7. So A equals 103.7 divided by 32, which gives us 3.24 metres per second squared. Okay, next one. Calculate the magnitude of force on box B by box A. So if we've got box B, we've got box B is pushing back on A, so that's F on A by B. But we've also got force from box A pushing on box B, so that's F on B by A. So the net force, F net, is equal to the force on B, F on B by A, minus the force on A by B. Now these can get a little bit wordy when you actually say things out loud, but essentially we've got our net force, F net, equals mass by acceleration, which we said was for box B, it's 12 times by 3.24 from previously, which gives us 38.88 newtons. Okay, so there we have, substituting that in, 0.88 is equal to F B by A minus the 54.1 due to our friction force from before. So therefore FB by A is equal to 93 newtons when you round it off to 2 sig figs. Righto, question 9. The OSIRIS-REx space probe sent to the asteroid Bennu to collect a sample and return to Earth. The probe reached the region of the asteroid in December. For the next 2 years, it will orbit the asteroid in order to study it from afar and calculate its mass. After making several hundred orbits around the asteroid in a month, the orbital data is, now that's diameter, not radius, and that's how long it takes, and we've got our tolerances here. So, first of all, the radius, calculate the mass of the asteroid. The radius is equal to diameter over 2, so that's equal to 3480 over 2. which is equal to 1,740 metres. Okay. Now, looking back at the main formula, r cubed over t squared is equal to g over mass that it's actually orbiting, so we'll call that central, over 4 pi squared. So that ends up being 1740 cubed over our period, which is 209,000. That's squared. That's equal to 6.67 by 10 to the neg 11 times by the mass of the object we're orbiting divided by 4 pi squared. Rearranging all of that, and you end up with mass is equal to 4 pi squared by 1740 cubed over 6.67 by 10 to the neg 11 times by 209,000 all squared, and that gives us a mass of 7.14 by 10 to the power of 10 kilograms. Shows that the percentage uncertainty of the orbital period is 0.43%. Must show you're working clearly. Okay, so the absolute uncertainty from up above was 900 seconds. Now our measured value, equals 209,000. So the fractional error is 900 over 209,000, which is equal to 0.0043, times that by 100 to give it to us as a percentage, and that gives us 0.43 cent. Part C says consider it as a sphere with a radius of 300. What would be the expected gravitational field? So gravitational field equals gm over r squared. So that's equal to 6.67 by 10 to the neg 11 times by the mass, which we've just worked out, 7.14 by 10 to the power of 10, and that's over 300 squared. So the gravitational field will be 5.29 by 10 to the negative 5 newtons per kilo, which seems very small, but given that it's only an asteroid with a radius of 300, we would expect it to be small, 5.29 by 10 to the neg 5. That's question 9.